Tension. What is tension? Tension. T-E-N-S-I-O-N. Tension. So, first of all, let's write the line, the random just line, okay? Line. So this line went through tension. Oh, damn. Okay. Then it turned into a longa. This is tension, and tension is sort of pull in the one word. Pull, and according to my lecture slide, it is say that stretching forces. Stretching forces. Forces. Okay. So on the other hand, what is the opposite of tension? This is compression. C-O-M-P-R-E-S-S-I-O-N. Compression. Compression. So also let's write the random line. And this line went through compression. Then it turned into shorter. This is compression, and compression is push in one word. And according to also a lecture slide, this is crushing forces. Crushing forces. Also, there's a word that deform. Deform. What is deform? Let's think about clay. Okay, first of all, this is clay, okay? Clay. And kids play with this clay. Kids played. So this clay turned into triangular. This is now triangular clay. This is deform. This is what the deform means, okay? In words, deform is changing shape. This means changing shapes. Okay. Also, let's think about balloon. Like balloon and change the shape, and also clay. Clay is the best example, and the dough. Lots of examples in our life, right? Okay. And the type of deformation depends on the type of force called force applied. So, yeah, like a type of deformation based on what kind of force it went through, tension or compression. Like it went through compression, it might become smaller. Then if it went through tension, it might become longer. So this is obvious explanation, right? Also, when a material is subjected to tension, its length will increase by a certain amount, which is called extension or elongation. Extension or elongation. They both have the same meaning, right? Elongation, which means when a material is subjected to tension its length will increase by certain amount. Its length will increase by certain amount. So when the material is subjected to tension, its length will increase by certain amount. So extension and elongation is just having the meaning of that in their word meaning, right? This is just the length will increase, and that is extension or elongation. Yay! Okay, let's now move to the author words. So it is especially important to understand the performance of materials and tension, as their tensile strength is usually lower than their compressive strength. It's especially important to understand the performance of materials and tension, as their tensile strength, compressive strength. Okay, this is obvious. So there is a different types of strength, okay? Strength. One is tensile, and another one is compressive. Then tensile is ability to resist tension. Ability to resist tension. So tensile strength is, there's a line, okay, and that line went through tensile, went through tension, but this line has also tensile strength. So tension is low and tensile strength is higher, then it will be turned into still the same. Okay? Does it make sense? This is tensile strength. Tensile strength. Okay. Then a compressive. What is compressive? This is ability to resist compression. No, very obvious, right? Ability to resist compression. So the line was also like this. Then there is compressive strength. Then it went through compressive strength is higher and tension is lower, so it won't change as well, like a similar length. But let's imagine it like a different way. Compressive strength is lower, tension is higher. Compression, this is not tension. I'm sorry, I made a mistake. So this is compression. Yeah. So compression will win, okay? Compression will win, so it will be shorter. Very easy, very obvious, right? And according to the slide, it say that the performance of materials and tension as their tensile strength is usually lower than their compressive strength. And mostly, tensile strength is lower than compressive strength, so it will be like this. This is winning. This compressive is winning. Yay! So, yeah. Some materials in tension as their tensile strength is usually lower than their compressive strength. Oh, yeah. This is obvious. So I talked about this tension, right? And during this tension, and this line has also tensile strength and compressive strength. So for that tension to go very well as planned, the tensile strength should be lower, so tension will happen. This is exactly what I talked about here. Yeah. I just got it. Oh god. Okay. Let's move to another topic. Elasticity and plasticity. Oh, I love this topic. So, some materials can extend significantly but still return to their original shape, and materials' ability to do this is called elasticity. Elasticity. So let's think about rubber band. Rubber band, that is used for hair, right? You are changing that shape and it turned into the first form. So this is elasticity. Yeah. Oops. Elasticity. Elasticity is rubber. Oops. Rubber. Example. This is example. Elasticity is hard to explain it. The best example is rubber, actually. Something turned into the original shape again. Yeah. So, able to extend significantly, obviously. But still return to their original shape. This is the main difference. Okay. Then let's think about plasticity. Think about, for example, just plastic or paper. Yeah, there's a big example, right? You hurted the paper, then trying to turn that paper into the original shape, and it could not. This is exactly what plasticity is. Okay? Able to extend significantly like it is. Able to expand significantly. Go down. Okay, I got it right again. Able to extend. Gently. But cannot return original shape. Yeah, exactly. And there's some words, stiff and brittle. What are they? Stiff. According to my lecture slide, is saying that if a material has a very low elasticity and is strong, engineers say it is stiff. Very low elasticity. This means very low ability to return their original shape. Okay, very low elasticity and strong. Strong. This is the main thing we should focus on, right? So what is brittle? Brittle is the real composite of this stiff. Brittle, B-R-I-T-T-L-E, brittle. It's sounding like brutal. It is not brutal. This is brittle. Brittle it has also very low elasticity. Elasticity and weak. Yeah, a stiff is strong, a brittle is weak. And the best example of brittle material is glass. Changing the ability of glass return to their original shape is almost impossible, and this is very easy to break that glass. And I'm thinking about this is the best example, right? The kid breaking their neighbor's window. So that is the best example, and that's because glass is brittle and window is made of glass. Yeah. And it's also saying and it fractures. Like fractures was in my previous class. Maybe I need to read that fracture mean again. It was maybe a little bit different than what's happening here, but yeah, I have explanation of and definition of fractures. Yeah, here it is. We had this class terms of properties of minerals and fracture, the property of mineral breaking in a more or less random pattern with no smooth planar surfaces. So fractures is also like a breaking. It fractures. Fractures. Break. Okay. And some materials can change shape significantly but do not return to their original shape. This is plasticity, and we say these materials are plastic. And a material that can be plastically deformed by hammering or rolling, for example lead PB, is called malleable. Okay, this is interesting. Here is new word, malleable. This is adjective. Adjective. This is a material. That can be plastically. Plastically is the big word because you can't use the word malleable in a elastic material. Yeah. Plastically deformed by hammering or rolling. I try to write much prettier these words, hammering or rolling, because these are important. An example is lead. Lead and the chemical formula is PB. Okay? And this is malleable. Then there's also the word ductile. D-U-C-T-I-L-E, ductile. And the ductile is a material that can be drawn out. Drawn out is stretched into a long length. And the example is copper, Cu. Okay? A material that can be stretched. And so you can use the word drawn out into a long length. Oh God. Into a long length. These are the important words. Long length. And this is example of copper, Cu. You know, the copper is very the common material. Also, this is element, right? Used in the what is this? I don't know how to explain. Wait. Electricity sharing? Huh? Oh yeah. Copper is used common in the electrical transmission. And if you know, coppers are mostly like this. I will try to draw. Copper is mostly yellow or orange, yellowish. And this is like this, okay? And like this, I think you guys have this a lot. And this is copper. This is copper. Yeah. And copper is able to be stretched into a long length, and so this means copper is ductile. Yeah, exactly. Okay, so there is stages in elastic and plastic deformation. Okay. Oops. Stages in elastic and plastic deformation. So I gotta try to draw this graph. And this graph shows the typical extension behavior of ductile materials in tensile testing. And this is the sample, okay? This is the graph I'm trying to draw. Ooh. Okay. Tensile. Load. Here it is. This is 0. And this is just like this. I'm drawing very bad, but okay. We just need to remember, okay? This is not a class, not exam for drawing. This is for English class. And 2 is 3 and 4 and 5. Yay. And 1 to 2, this is elastic deformation. Elastic deformation. So it means from 1 to 2, it turns into the original shape. Turns into original shape. So basically, the yield point of this graph is 2 voiding. This is yield point. What is the yield point, okay? This is the right time to think about balloon. This is balloon, okay? So, like, what is the word? I forgot. Okay, blow up balloons. Okay. Okay, balloon was like this, okay? God. Then air goes into the balloon, air. Then it turns into big, more big. Then pump. This is the yield point of balloon. Yeah, this is exactly what I wanted to explain. Yeah. So after the yield point, this balloon cannot turn into this shape. This is not possible because of yield point. Okay? I hope it was very understandable. By the way, it was very understandable to me. So I just gotta read what is said on my lecture slides. Okay. Points 0 to 1. The extension of the bar is proportional to the increase in tension. For example, when tension increases by 10%, length increases by 10%. Okay? And the point 1, the bar reaches the limit of proportionality. Beyond this point, length begins to increase at a slightly greater rate than tension. Point 2, the elastic limit is reached. Beyond this point, the bar will no longer return to its original length. In many materials, the elastic limit occurs almost immediately after the limit of proportionality. And point 3. Oh, it is said that yield point happens in the point 3. Not this. Okay, point 3. Point 3. The bar reaches its yield point. Once it yields, it continues to increase in length even without a further increase in tension. Point 4. This is the ultimate tensile strength of the material. Beyond this point, a vast, narrower section appears at a point along the length of the bar, signaling that it is about to fracture. Signal fracture. No, it's about to fracture. You know, guys, the fracture means break. Point 5, this is the fracture point where the bar breaks in two. This is fracture point. Fracture point. Okay. I think that's it. So, here are some questions, including a stretching force is called what? A stretching force. What is a stretching force? The first. The second, a crushing force. What is crushing force? What is the name of it? Extension. Extension is also called. The fourth, tension causes. Tension causes what? Tension or compression causes sorry. That was my bad. Cause what? Okay. Stretching force. I was very not understanding what was it asking. Okay, when I was learning for the first time, I could not understand. It was asking about tensile strength or tension. Then it was tension because it is saying exactly that this is stretching forces. Okay. Okay, it's saying this is stretching forces, but so because it's saying stretching forces and this is tension, so this is tension. So a crushing force is compression. Obvious. Oops. Compression, and it's exactly the same crushing forces. Compression and extension is also called. Here it is. There's two words, right? Extension. Here it is the thing asked, it was in question, it was in blank, and we have to write elongation instead of blank. So extension is also called elongation. Tension causes. Tension causes what? Tension causes elongation or extension. Where is that? Yeah. When a material is subjected to tension, its length will increase by a certain amount. It's exactly same here, right? When a material is subjected to tension, its length will increase by a certain, then extension or elongation happens. Extension or elongation. So the last question, tension or compression causes. So we had talk of it the first very early, by the way. Yeah, deform. Here it is. Deform. I talked about a circle, triangular turning into triangular clay. Circle clay turning into triangular clay because it's changing shapes and because of tension or compression. Okay, so this is deformation. Yeah, so like this short line turning into a longer line, the deformation is happening here. And also this long line turning into a short line, also deformation is happening. So compression and tension cause deformation. Okay, I hope it was very understandable. Okay, here it is. Also another questions. It's about matching words. So I gotta just read the correct matching. If a material is stiff, it has low elasticity and high tensile strength. It was in this class. It's saying that if a material is stiff, it has low elasticity and high tensile strength. And high tensile strength. So that means it's strong. Then next, if a material is brittle, it has low elasticity and low tensile strength. If it's brittle, it has low elasticity, they are same, and low tensile strength. Yeah, like I could not find it correctly because I just remembered strong or weak, but high tensile strength is equal to strong and the low tensile strength is equal to weak, okay? The next, if a material is plastic, it is malleable or ductile. We had conversation about it. If a material is plastic, they are malleable. Malleable is a material that can be plastically deformed by plastically deformed by hammering or rolling. Lead, and the ductile is a material that can be stretched into a long length copper. The fourth, if a material yields, it has been significantly plastically deformed but not broken. I did not know this. I think we have to write this, okay? If a material yields, it has been significantly plastically deformed. Deformed means changed shape. But not broken. If a material yields, I really have to remember this. If a material yields, it has been significantly plastically deformed, but not broken. Okay. Fifth, if a material fractures, it has been loaded beyond its ultimate tensile strength. Yeah, this is obvious, right? If a material fractures, it has been loaded beyond its ultimate tensile strength. It broken. Yeah. And six, the last one, if a material is elastically deformed, it has been extended to a point before its elastic limit. It has been extended to a point before its elastic limit. I think we have to write this too. Like, I don't understand. If a material is elastically deformed, it has been extended to a point before its elastic limit. If a material is elastically deformed, it has been extended to a point before its elastic limit. If a material is elastically deformed, it has been extended to a point before its elastic limit. Okay, if a material is elastically changed the shape, it has been extended to a point before its elastic limit. When a elastic deformation turned into reach the elastic limit, it can't turn the original shape. So before its elastic limit, it has been extended to a point. Okay, so well, this is a rubber band. Then you changed it like this is extended to a point, and this is also elastically deformed. But it also could turn into the original shape, and this is exactly what is this sentence is trying to explain, in my understanding. Yeah, I hope it was correct. Okay, and I have very long passage, paragraph, and yeah, I think just reading this is okay. All right. So, how are the springs used in a car? Suspicion made springy. Do you guys know spring? Spring? Yes, spring is season, right? Season. Like after winter, before summer. But also, the second meaning of this word is the springy thing inside of the car. I think you guys know about it. Like something like this. Or like this. And which is used in a car. Sorry. I was always bad at drawing car and I almost know nothing about car. And inside of the car there is spring. And it's asking that how are the springs used in car? Suspicion made springy. So why spring is springy? Why springy? How? So we gotta learn about it from this paragraph, okay? It sounds like a silly question, yeah. But think about it for a moment. Okay, we talked about it a lot. In order for a spring to compress or extend, then return to its original shape, it must be elastic. Yeah. So, the spring is elastic, baby. Elastic. And elastic is able to return to its original shape. This is spring is a material. This is able to return to its original shape. But springs are made from wire. And wire is made from very ductile metal. So, this spring is made of wire. Wire is something like, I draw this like along this line, and this is ductile. And ductile is the material that can be lengthened, and a biggest example is copper, a material that can be stretched into a long length. Yeah. So, made of wire and ductile, so this is kind of plastic, right? And when the wire is manufactured, it is not only stretched beyond its elastic limit, meaning it will no longer return to its original length, but also beyond its yield point, where significant irreversible extension, elongation, or deformation occurs. Yeah, so like ductile, when after elastic limit or yield point, it cannot turn into its original shape, right? This is not possible. So, the metal from which springs are made has therefore been plastically deformed. Yeah, so wire is plastically deformed. and consequently needs to have its springiness put back. To do this, once heated and kept at a high temperature for a sustained period, this resets the atomic structure of the metal, partly at least, so that after tempering, the spring will behave as it should. It can be elastically deformed and will subsequently return to its original shape. Oh, it's so interesting. Yeah, so wire went through. It should be like go through a different color. Wire went through manufacture. And it formed into coil in a smaller piece, and it is tempered. Tempered means a process which is heated and kept at high temperature. Which means tempered means heated, like in a high temperatures, and kept at high temperature. Kept at that high temperature. And this is manufactured. And for a sustained period. Oh God. For a sustained period. So this resets the atomic structure of the metal, so that after tempering, this spring will behave as it should. It can be elastically deformed, so it turns into elastic. Deformed and will subsequently return to its original shape. Whoa, this is so cool, right? So in this paragraph, we learned about why spring is springy. Like, springy means like the wire can turn into like its original shape, right? Wire was like this. Then turning into this. Oops, why it's not writing? Oh damn. Turning into this. Then turning into this. This is what is springy. Okay. And basically the elastic spring is elastic, able to return to its original shape, but spring is made of wire, and my wire is very ductile material. Ductile is able to strengthen into the longer, and wire is plastically deformed. This is a plastic, but this wire goes through manufacture, so it can be formed into coil and tempered. And tempered means heated and kept at that high temperatures for a sustained period, and it turns into elastic. Oh wow, this is very cool. Okay, now my explanation is finishing up, and thank you.